One of the most complicated concepts in distributed databases is the consistency model. Many senior developers need help understanding the differences between eventual and strong consistency, the two major consistency models in distributed systems. Today I will explain and illustrate the distinctions. Take a look. Let's consider a database cluster with 4 nodes or servers. In the following animation, each sphere represents a node in a different physical location: New York, London, Dubai, Tokyo. When new data arrives, one of the nodes in the cluster is responsible for committing the transaction without interfering with the others. Soon, the replication process will be kicked out. However, for a short moment, this creates a situation where the different nodes will represent a different state. In other words, users from various locations at the same time will see different states or results. Eventually, all the nodes become consistent with each other until new data is coming. If the system is continuously changing, there is no moment when all the users from all the locations can see the same data. There are applications where this is acceptable. For example, if the exact number of likes under a post on social media platform will be a bit later available for different locations is not an issue. In return, the system will be stable and highly available. Obviously, there are critical applications where this behavior is unacceptable. Stock trading platforms cannot afford to show different data in distinct places at the same time. This is where strong consistency comes into play. The cluster implements a global commit for a given transaction when new data arrives. This results in a consistent state at every point in time. The way how it works, the cluster simply does not expose the new state until it has verified that all servers have the most recent data. This guarantees a single global agreed upon order of operations across all replicas. Strong consistency prioritizes consistency over availability and may introduce additional latency and potential service disruptions in the event of network partitions.